Welcome to this comprehensive explainer. If you're a back-end engineer gearing up for an interview, or maybe you're just looking to seriously level up your system design skills, well, you are in the exact right place. Today, we're going to crack the REST API interview gauntlet. We're breaking down everything from the absolute bedrock foundations all the way up to those advanced architectural patterns that literally separate mid-level developers from the true senior engineers.
Okay, before we get into the deep technical weeds, let's look at a concept that works perfectly even in non-technical stakeholder meetings. Think of a REST API like a waiter in a restaurant. You, the client, you can't just barge directly into the kitchen, right? Instead, you tell the waiter what you want from the menu, and they bring it out to you. That menu, that's your API documentation. You ask for something, that's a GET request. You order something brand new, that's a POST. Or maybe you send something back, which is a delete. Honestly, it's just the perfect analogy for client-server separation. So, here is our game plan for this explainer. We'll start with mastering REST foundations, move into verbs, nouns, and statuses, tackle securing your API, jump into some real-world API scenarios, and finally wrap the whole shebang up with advanced architectural patterns. Let's dive in. All right, Section 1, Mastering REST Foundations. Because let's face it, every technical interview starts right here, testing your bedrock fundamentals. To be truly considered RESTful, an API absolutely must meet 6 strict architectural constraints defined by Roy Fielding way back in the year 2000. So you've got client-server separation, cacheability, a layered system, a uniform interface, and an optional one, code on demand. But the crucial point here, the one interviewers will absolutely grill you on, is stateless. Stateless means each individual request has to contain every single piece of information the server needs to process it. The server stores 0 client context between requests, literally no server-side sessions. Next up is a classic showdown, REST versus SOAP. Now, REST is an architectural style that typically uses JSON over HTTP, and it heavily leverages native HTTP caching. It's lightweight, it's super performant. SOAP, on the other hand, well, it's a strict protocol. It uses XML exclusively, defines its own custom messaging format with envelopes and headers, and yeah, it has a much higher overhead. It definitely brings back cold sweats of endless nested tags for some of the older developers out there. But actually, don't dismiss SOAP entirely. It still has a very real place in enterprise systems that require formal contracts like WSDL or really strict message-level security. Okay, let's move right along to Section 2, verbs, nouns, and statuses. This is where we get into the tactical weeds of URIs and those tricky status codes. When you're evaluating core HTTP methods, you absolutely must understand 2 vital concepts, safe and idempotent. Safe methods, like GET, well, they don't modify resources. But idempotent? That is the magic interview word right there. An operation is idempotent if performing it multiple times produces the exact same result as just doing it once. GET is idempotent. Delete is idempotent. I mean, deleting a user once or 10 times still leaves the user deleted, right? Put is also idempotent. Post, however, is not. Because if you send it twice, you're going to create 2 completely separate resources. And that brings us to a massive interview gotcha. Put versus post. With post, you're creating a new resource, and the server determines the URI. Like you post to /users, and the server comes back and says, great, here is /users/123. Put, however, replaces a resource at a specific URI that the client actually specifies. You put directly to /users/123 to replace that entire resource. If you only want to partially update something, well, that's when you'd use a patch method instead. Let's test your architectural maturity for a second with some status codes. What is the actual difference between a 400 and a 422? So a 400 bad request indicates malformed syntax. Imagine a trailing comma that completely breaks the JSON structure. The server physically cannot parse it. A 422 unprocessable entity, though, means the JSON syntax is perfectly valid, but it fails semantic validation. For instance, the JSON is totally correct, but the string you provided for an email address, it just isn't formatted like an actual email. All right, we're entering Section 3, Securing Your API. Security is the ultimate gatekeeper in system design rounds. I literally see senior engineers mix these 2 up constantly in code reviews. 401 unauthorized actually means unauthenticated. The server does not know who you are at all, and it's basically prompting you to log in. 403 forbidden, on the other hand, means authenticated. The server knows exactly who you are, but you just lack the necessary permissions to do what you're trying to do. Trying to re-authenticate is not going to help you out with a 403. So how do we actually prove who we are?
We generally rely on 4 main authentication types. You've got API keys, which are simple and great for server-to-server communication, Bearer tokens, used for stateless session auth, OAuth 2.0, which is your go-to for delegated third-party access. And hey, quick pro tip here, under the new OAuth 2.1 standards, PKC, Proof Key for Code Exchange, is now mandatory for all clients. And finally, we have JWTs for stateless, self-contained authentication.
Let's look a little deeper at JWTs, or JSON Web Tokens. They consist of 3 parts: a header, a payload, and a signature. The server signs the token and clients send it along with their requests. Because of that signature, the server can validate the token without ever doing a database lookup, which is incredibly powerful. But here is a critical security tip if you're working with distributed systems. Always use RS-256, which uses asymmetric public and private keys, rather than HS-256, which just uses a single symmetric key. Doing this prevents algorithm confusion vulnerabilities if multiple services need to verify those tokens. Okay, transitioning into Section 4, Real-World API Scenarios. We're moving from definitions to application now, basically mimicking a system design interview loop. So a really crucial point when you're returning large lists of data is how you handle pagination. Offset-based pagination is super simple. You just say, skip 40, give me the next 20. But it has absolutely terrible performance on massive data sets. Why? Because the database still has to manually scan through those first 40 rows. If you want to build systems like Stripe, GitHub, or Slack, you have to implement cursor-based pagination. You pass a specific pointer or a cursor, and the database fetches the next set of records directly from that specific index. It is highly performant. Let's see how this all comes together in a classic interview scenario: designing a hotel booking API. How do you prevent total disasters? Well, as we just learned, you'd use cursor pagination for searching through thousands of hotels. To prevent 2 people from booking the exact same room, you'd implement optimistic locking, returning a 409 conflict status code if a double booking is attempted. And for the payment step, you absolutely must use idempotency keys. The client generates a unique UUID and sends it with the payment post request. If a network blip causes the client to send the request again, the server sees that key, knows it already processed that exact payment, and just returns the cached success response rather than charging the poor customer's credit card twice. And here is a notorious backend killer you just have to know: the N+1 query problem. This happens when you fetch a list of records, let's say 100 users, and then, as you loop through them, your code executes a brand new database query to fetch the posts for each individual user. Think about that. That is 1 query for the users, plus 100 separate queries for the posts. That's 101 queries. It causes massive performance bottlenecks. A true senior engineer solves this by using prefetching or join loads in their ORM to grab everything all at once in just 2 queries. Let's see how all of this builds into our final section: advanced architectural patterns. This right here represents the true mastery stage of your developer journey. How do you handle a request that takes, say, 5 whole minutes to process, like generating a massive report, without timing out the client's HTTP connection? You use the asynchronous request pattern. First, the client sends a post request. Second, the server immediately responds with a 202 accepted status code and includes a special status URL in the location header. Third, the client just occasionally pulls that new status URL. It might return processing a few times, until finally it returns completed along with a URL to download the finished report. What about migrating from an old API version 1 to a brand new version 2 in production without breaking any of your existing client applications? For that, you employ the Strangler Fig pattern. You literally deploy V2 alongside V1. Then, you route all new features to V2. Next, you gradually migrate those existing endpoints over. To communicate deprecation to clients who are still lagging behind on the old system, you send a sunset header. Finally, once everyone is successfully migrated off, you safely remove V1. Now, handling transactions across distributed microservices presents a massive challenge. You can't just simply lock a database across 3 completely different servers. Instead, you use the Saga pattern. Each service executes a local transaction and then publishes an event. For example, order created, payment processed, inventory reserved. If a step fails anywhere along the line, say that inventory reservation fails, it triggers what we call compensating transactions backwards. It publishes an event to release the payment, and then another event to cancel the order. So we have spent this entire explainer mastering REST.
But to demonstrate true senior-level architectural maturity to an interviewer, you need to be able to answer this one provocative question. When should you not use REST? Look, REST is absolutely incredible, but a master engineer always picks the right tool for the job. If you're building a real-time chat application or a multiplayer game, you shouldn't be using REST at all. You need the bidirectional streaming capabilities of WebSockets. If you need incredibly high-throughput communication between internal microservices, you should be reaching for gRPC. If your client needs to query complex, deeply nested data structures without making dozens of round-trip requests, GraphQL is your answer. And for heavily event-driven architectures, you want to rely on message brokers like Kafka. Understanding how to build a perfect REST API is vital, absolutely, but knowing exactly when to step outside of it, that is what gets you the job. So looking at your current projects, are you forcing REST where another pattern might be the secret key to unlocking your system's true performance? Think about it.